Table 1 represent a truth table for a logic circuit. Use it to answer the questions that follow. Then we have table 1 here. Table 1, we have this truth table. The truth table has 3 inputs, and the third one is the output. L is the output. L is the output. So from this table, we are told Roman 1, derive the Boolean expression for the sum of products. And second question, use K-map to simplify the Boolean expression. So let's start with Roman 1, deriving the Boolean expression for the sum of products. So when deriving an expression or a Boolean expression from a truth table, you only consider the rows. You consider the rows that have an output of 1. You consider the rows with output of 1, and what you do, you write the equivalent ANDed expression, what we call the ANDed expression for the particular row and all the rows. So we consider only the rows with output of 1, and you write the ANDed expression for that. After that, you do what you call ORed all the expressions that we have written for all the rows. ORed means you sum. So let's start by writing the ANDed expressions for each of the rows with output of 1. So when we consider this row, you find that A is complemented, because A, the normal A logic should be 1. So N0 represents not A. So the inputs here, you only write for the inputs. So here the input A is having a bar, B is not having a bar. So if we have 1, you don't write a bar. If we have 0, you have to indicate a bar. So in this case, we have not A, B, and not C. The other one will be having A, not B, not C. The other one will be having A, not B, and C. The other one will be A, B, and not C. And the last one will be A, B, C. A, B, C. So these are ANDed expressions for the outputs of 1. So you only consider where the output is 1. Then after that, you ORed them, and when you add, ORed is meaning you sum, and when you sum, you get what we call sum of products. So in this case now, for the Roman 1, you will get an expression which is not A, B, not C, or A, not B, not C, or A, not B, C, or A, B, not C, or A and B and C. So this is the expression that we are told to derive in Roman 1. Then after that, we are told to simplify it using K-map. So our expression is, let's write it in full, Roman 1, whereby L, which is the output, L will be not A, B, not C, plus A, not B, not C, plus, in logic gates we use plus is an or, so we can say or A not B C, or AB not C, or A B C. So that is the expression for the Roman one. Now we simplify this using K-map Roman 2. So K-map is just the same logic for a truth table that we translate it to a table. So the same way we determine the rows of a truth table by using the formula 2 power n, where n is the number of inputs. For the K-map, we use the same formula to determine the number of squares. So the number of squares in this case, we have 3 inputs. The number of squares will be 2 power 3, which is 8. So we draw a table of 8 squares. So this is how we draw it. Eight squares. So that is the table. Note how I label the 3 input K-map. So this at this column, I will label. Let's say we have A B, not A not B. We have not A B. We have A B. We have A and not B. Here we have not C and C, such that when we combine in each square, we have a combination of, when we join this and this, we have to form the expressions of 3 variables. Remember, this is the same as whatever is in the truth table, because for example, let me proceed, and I'll show you how this can be gotten from the truth table, how we relate it with the truth table. So in K-map, we map the expression in it, and mapping the expression meaning or means we look at the square that corresponds to each of the terms, and we write 1 at that particular square. So for example, the first expression is not A, B, and not C. So we look at the square that is the intersection of not A, B, and not C. So not A, we have here, we have B, then we join with not C. So we indicate a 1 here. We indicate 1 there. Then the second expression, not A, not B, not C. So we look at that square. We have A, then not B. So A, not B, and not C. So we have another one here. We have also the other term is A, not B, C. A, not B, C, A, not B, and we have C. So we have a 1 here. Then the other one is A, B, not C, A, B, and not C. It's that one. And we have A, B, C, and A, B, C will be this one. So from that point now, after mapping the expression by indicating 1 in every square that is represented by our terms, you look at the complete loops in the K-map. So in this case, In the K-map, we have this loop, and we have this loop. We have those two complete loops. So let's now proceed. In the first loop, the expression is, for this point, the expression is not A, B, and not C. And this one represents not, that is A, B, and not C. And these two, remember, they are red. We have a plus. So using K-map now, here we use Boolean laws, whereby we know from Boolean laws not A or A, sorry, not A or A gives us a 1. So it means this A will cancel with this A. And we don't have any other two cancelling. So it means we have to remove not A and A. We remain with B and C. B and not C. So the resultant of the first loop is B and not C. Then when we consider the other loop with 4 ones, it will be having A, B, not C. This is this. Then this one will have A, not B, not C. Then this one will have A, not B, C. And this one has A, B, C. So these four, when you consider addition for them, or logic addition, you'll find that when you consider these two, this B will go with that B. Also, this B in here will also go with that B. Also, we have not C will go with this C, and this other not C will also go with this other not C. So these four expressions, we only remain with A. And that case, now, of using the K-map, we'll get the answer as A or B and not C. So the expression simplified using K-map, L will be equals to A or B and not C. So get more questions, practice, and get used to K-maps, because also this is a very testable part in the exam.